MacMaths, let's do some maths today. Okay guys, here we go. We're working from this book, Statistics and Mechanics, but I'm going to cover the mechanics lessons in this unit. So we were starting from chapter 8, and this follows on from my series on the pure AS, so this is year 1 of A-level. The mechanics section then now in the new A level, it goes through the lesson 1. I'm just going to go through this first chapter, which is an introduction to mechanics, and I'm going to go through SI units. I'm going to look at mass versus weight. I'm going to look at assumptions, and I'm going to look at some of the forces that we're going to use. I'm not going to go through any of the questions in that chapter 8. They're fairly straightforward. You can do that just from reading the information from this lesson here. There's some questions on vectors, so the work that we've done on vectors, the lessons that we've done on vectors is enough to get you through that chapter. Okay, so let's start then. Let's start with SI units. So SI units, it's the S and the I stands for system and international. It's French. You know, in French they say sentences the other way around. So if I said system international in a French accent, there you'd have it. There are our SI units. And the SI units that we're going to use throughout mechanics are for mass, are kilograms. So we're only going to use kilograms. If you get a question with grams in, change it to kilograms. We're going to look at length or distance, and that's going to be in meters. So if you get anything else in kilometers or centimeters, change them to meters. And time, get anything in hours or minutes, change them into seconds. So those are the SI units that we're going to use. So all of the questions, we're going to use kilograms, meters and seconds. That means that if we get a question talking about a train traveling at 30 kilometers per hour, so 30 kilometers for every hour, what we're actually going to do before we start doing the maths on that is change kilometers into meters. So 30 kilometers would be 30,000 meters, for instance, and it would be traveling 30,000 meters in 1 hour, and 1 hour is 60 times 60, so it's 3,600 seconds. So we would then say 30,000 meters in 3,600 seconds, divide them both by 3,600 to find out how many meters it travels in 1 second. This is why they're called units of speed or velocity, because the word unit means 1. So how far does it travel in 1 second? And divide that by 3,600, and I think you get, done that before, I think you get 8.3 recurring, so 8 1/3. So this would be 8 1/3. We talk about this train travelling a speed of 8 1/3 meters per second. You'll see it written like this, or like that, wouldn't you? Meters per second. Okay, so those are the units we're going to use, kilograms, meters and seconds. So change everything into those 3, please, when we do the maths. The next thing, that sticking with units actually, and I've just wrote down meters per second, so I don't know whether you've ever really sort of thought about that. People just sort of accept it, but just very quickly, just in case you do sort of think about it, why do they sort of do it like that? If you travel, let's have a look at speed to start off with. If you travel from A to B, which is 6 meters, a distance of 6 meters, not very far, the length of a long living room. If you travel from A to B and you travel that distance in 3 seconds. Okay, if you do that, well, how far are you traveling in 1 second? So we split that up. You can see that for every 1 second, every unit, 1, we're traveling 2 meters. So that's why we would call it 2 meters per second. And how do we get that 2 meters per second? We do the distance divided by time. So 6 divided by 3 is our 2. Well, that is, of course, 6 meters divided by 3 seconds. 6 divided by 3 gives us the 2, and the meters divided by the second, meters divided by seconds. So you see it written like that, but we tend to write it, don't we? That S is on the bottom, we move it up, so it's to the power of -1. So that's why it has that ms, m times 1 over s. That is what it means, because it's the meters divided by the seconds in the original calculation. If we look at acceleration, I hope I've spelt it right, I have, and we are accelerating from A to B, constant acceleration this time. So let's have a speed at A. Let's say at A we're travelling at 2 meters per second, but over 3 seconds we increase that, and by the time we get to B we're travelling quite a bit faster, same speed as that train, 8 meters per second to the -1. So in that time you can see that our speed has changed by, not 6 meters now, by 6 meters per second. We're going 6 meters per second faster, and we've done that over, we've said 3 seconds, 3 seconds later. Okay, so this timeline is 3 seconds long. So acceleration is how much you increase your velocity or your speed for every one, every 1 second. That's units again, that word units. So this is at this point 2, then we're going at 4 meters per second, we're going at 6 meters per second, we're going at 8 meters per second. So we've increased by 6 meters per second. We're increasing by 2 meters per second every second, aren't we? Okay, that's 1 second. So 2, 4, 6 and 8. And the way that we got that, this 2 meters per second increase every second, is we go 6 divided by 3 again. Okay, we split that up into 3, and 6 divided by 3 gives us 2, but this time we've got meters per second to the -1 divided by seconds, haven't we? And this combined gives us the units for acceleration. S to the -1, we can move that S back down to the bottom, this S to the -1, and we can get rid of the -1 then, and we'd have S squared on the bottom. Or we can move that up, and we can write it, as mathematicians do, as 2 meters per second to the -2. So this is accelerating at 2 meters per second to the -2. This is a constant speed of 2 meters per second. The difference between speed and velocity, as you know, velocity has a direction. Well, we're not talking about any direction, we just talk about speed. Okay. Mass versus weight. Let's talk about mass versus weight. We use that word in the UK, we use that word weight, when really, in everyday life, when really we're referring to the mass, the weight of a person. Might be, say, 50 kilograms, 60 kilograms or something like that, but really we're talking about their mass. I just want to first of all draw you a little diagram of me being very strong. There's a boulder, big heavy rock, and there's my hands and arms, and there's my legs, and I'm pushing that boulder, and when I push that boulder and I'm applying a force to it, there's its mass, and if I'm strong enough and it starts to move, it starts to accelerate in that direction. Well, Isaac Newton came up with a little formula linking those three things together: force, mass and acceleration. F equals ma. And this is the difference, this is what connects sort of mass and weight, really. If you take the mass of something and you times it by an acceleration, it gives you the force that mass is producing in its movement, and that is what we call weight. So that is that when we talk about the weight of someone, we take their mass and we times it by the acceleration. If I show you this diagram that I drew very quickly, you can tell I drew it very quickly. It's two sets of scales, and if I take a 3 kilogram weight, there it is, and stick it on the scales, of course the arrow is going to ping round to the 3 there, isn't it, to tell me that that is 3 kilograms. If I take my scales and my weight and go into a spaceship, this is not sight, so into a rocket and travel to the moon and do the same on the moon, and nothing's changed. The scales is the same, the block of lead or metal, whatever I've got that's 3 kilograms, is the same. But when I stick it on, when I'm sat on the moon, there's the moon, and this one is on the Earth, then this will only sort of ping round to about here, about 500 grams. And that's because, although it's the same mass, on the moon, the gravity is about 1/6 of that on the Earth as it is on the Earth. So instead of acting at about 10 meters per second squared, that's what acceleration is. You drop something from the sky, everything, no matter what mass it is, will accelerate down. If you ignore air resistance, it will accelerate down at about 10 meters per second squared. We do it a little bit more accurate than that. We usually use 9.8 in mechanics, in the mechanics chapter. But sometimes we just, as a rough guide, use 10 meters per second to the -2. And that's the weight of it. So this, when we talk about the weight of it, include the force that's this 3 kilograms is acting down, is that times 10 on the Earth, but it's that times 1/6 of that on the moon. And so the scales would need to be adjusted to reflect that. So it's the scale that would need to be changed so that this registers, it tells you it's 3 kilograms, to take out the effects of gravity on the Earth and gravity on the moon. And of course, if we, I don't know why I'm doing this, there's a black hole and this is the event horizon, and if we did our little experiment there as well, and that 3 kilograms would seem as a whole lot heavier, the weight of it would be approaching infinity, as nothing escapes, does it, from the event horizon at that point there. The pull would be a lot more than on the moon or the Earth, okay, as it's getting sucked into that black hole, okay. So that's mass and weight. So mass is a measure of, I don't know what it's a measure of, it's a measure of something, but when we times it by the acceleration of gravity, we get the force that it puts on any surface. And so let's have a look at the units for that, because we are talking about units. We take the weight of something, SI units, we use kilograms, and we times it by gravity, which is the acceleration, which is that. We get the units for weight, which is kilograms meters per second squared. So those are the units for weight, the weight of something acting down, and that is a bit of a mouthful. Okay, that's a bit of a mouthful. So we change that. So when we take our 3 kilogram weight and we times it by 9.8 to get, what would that give us, 29.4. Instead of writing kilogram meters per second to the -2, kilograms times meters per second to the -2, we change all of that and we give it an N for newtons. Much easier to say, and that's why we do it. So the force that something acts, down, the weight of something, we're gonna, or for all forces, we're gonna use N for newtons. And a lot of times it's mass times the gravity. Okay. So units for force is going to be newtons. Assumptions that we're going to make. So we've done, tick these off. We've talked about our units very briefly. We talked about mass and weight. We can get rid of that little picture of me now. Seems a shame, doesn't it? Such a good drawing. Look at the assumptions. Okay, let me think about the assumptions we're going to use. Right, so the assumptions that we're going to use, if we are, another little diagram there, that is a cannon, and it's going to fire a cannonball. Let's do a cannonball in blue, and that cannonball is going to fly and it's going to land here. If we want to look at how far that cannonball has flown, where does it start from, where does it finish? Does it finish at that point? Does it finish at that point? Where does it start? Does it start there? Does it start there? So what we do with mechanics, we talk about objects often as particles, the centre of gravity of something. So the centre from there to there is how far it's moved. So often, just to make things simple, when we're talking about an object, they will just talk about a particle. That's the point at where it is, you know, the centre of that point. So we think infinitely small or a particular point. So things are often modelled, objects are often modelled as particles. That's one of the assumptions that we make, so we can pinpoint where it exactly is at any point in time. Objects as particles is one assumption. Another assumption is, as that often used, as that cannonball is flying, it's going to hit some air resistance, isn't it? That it's going to slow it down, air resistance. And as it travels through the atmosphere, and in most parts we're going to put the air resistance is 0. It's not true in real life, there is air resistance, but we're going to ignore air resistance. That's another assumption that we're going to make. It is going to affect where it lands. It's going to land slightly less than what our model predicts, because we're not taking into account air resistance, but that amount is so small we're going to ignore it in most cases. So we're going to ignore air resistance. That's another assumption. And finally, an assumption that we're going to make, there's other ones that I'll talk about as we come across them, but these are just the main three, is as that cannonball is sliding out of the cannon, it's being restricted again by friction on the cannon, the sides of the cannon, the walls. And although we are going to deal with friction in the mechanics chapters, sometimes we talk about surfaces being smooth. So this is a block that's sliding, a force is applied that way, and it's sliding along this surface. Now, as it slides along the surface, friction is a force, isn't it, that resists the motion of two surfaces together. And as it's sliding along this surface, friction is going to be acting, I use FR for friction, is going to be acting in the opposite direction to what it's sliding. If we say that if that frictional force is very small, it's not going to affect it that much, we describe the surface as being smooth in mechanics. If you see that word smooth, it means we're assuming that there's no friction. There's not really a case in life where there's no friction. You think about ice is smooth. Ice might be smooth, but there is still friction there. But we're going to ignore that friction. And likewise, if you spin a wheel, it will spin round and round and round. But at the centre of that wheel, the ball bearings are spinning round, they've been well oiled and so on. There's going to be friction that will slow your wheel down, and a little bit of air resistance as well. But we're going to ignore those. So if you see that word smooth, that means we're ignoring friction. We are going to be using friction as a force in some cases, in some questions. So those are assumptions. If you see the word smooth, assume no friction. Treat objects as particles in most cases, so we can pinpoint their exactly where they are. And we're going to ignore air resistance. Those are the main ones. And finally, just a few seconds, talking about forces. If you put this pen onto my desk, it doesn't collapse through, it stops still. But on my desk, that pen, there it is, that's actually quite a good drawing for a pen. That pen, mass times gravity, there's its weight, is acting down. Now it's not moving down, and that is because the tabletop is imparting an equal and opposite force on my pen, and we call that a reaction force. Everything has a reaction force that acts down on a surface. There's a reaction force. If that reaction force didn't exist, then it would collapse through. If that reaction force is more than the weight of the pen, then it would go up, and it doesn't, it stays still. So it's an equal and opposite force, very important. So if we had a car on a road, okay, there it is. The first force that a mathematician would put in is the weight times gravity, the mass times gravity, sorry, to give you the weight of the car. That's what the car is acting down on the surface of the road, but that road is not collapsing, and that is because the road is given an equal and opposite force. So on the roof of the car, you'll see an arrow pointing directly up, perpendicular to the surface, with an R, capital R on it for reaction force. So we have a reaction force. Friction we've talked about, frictional forces is another force you're going to come across. And then the last one, back to a little drawing I'm going to do for you, again of me. There's me going for a walk. And when my girls were younger, I'd be holding hands with them like that when they were little. There's little Molly's hand there, and there's her little head. It's a bit bigger now, her head, and there she is. And as I'm walking along, holding hands with Molly to keep her safe, it feels to me that she's pulling away. I'm actually pulling her a little bit, and that is called a tension. There's a tension in our arms, so it feels like it's a pulling away from an object. To her, of course, that tension feels like it's pulling away from her. I'm pulling her, so it feels it's going in the opposite direction to her. And that's the tension in our arms, and that's a force that we use a lot in maths. You'll see pulleys like this with a block and a piece of string going over and then to another piece of string, and we're going to look at situations like that, a pulley, and we're going to release that, and if one of these is heavier than the other, it's going to move. But actually there's a tension in that string, and that tension acts away. It feels to this block, this is mg acting down, and this will be a mass time, its mass times gravity, and its mass times gravity, a different mass, but the gravity is the same. So that tension is acting away from that block, but the tension feels that it's acting away from this block as well. Tension is the same in the string, it's the same piece of string. So we're going to look at tension, and that is if you pull a piece of string, a block, pull in another block, then it creates a tension away from both of those blocks as you're pulling along, think of dragging someone along. So that's tension. If that tension also exists in if I draw it very quickly now, in a tow bar, and it's important to show you this one. I'll exaggerate the tow bar longer. Tow bar now, and this tow bar is going to be pulling a caravan. Caravans dreadful things, aren't they? The only time a caravan is great is when you're in a tent. But there's our caravan. Now as that car is moving, it feels to the car, it creates a tension in the tow bar, and it feels to the car that tension is pulling away. It's pulling the caravan is pulling away from the car, but to the caravan the car is pulling away, so the tension is acting the opposite way. So when we look at a caravan, we deal with just the tension pulling that caravan. When we deal with the car, we deal with the force pulling the car, that's the engine force, and the tension pulling away. We deal with them sort of separately. But the reason I showed you this diagram is because when that car hits the brakes and starts to slow down, then you've seen those cartoons where someone stops and everyone piles into them. This now is pushing in, and instead of pulling on that tow bar, it compresses that tow bar. These tension forces switch round, okay, and now to the car, the caravan feels like it's pushing against the car, and to the caravan who wants to move forward, the car is stopping it, so it's pushing against the caravan. That is called thrust. Okay, so in a piece of string, pulling away is tension, pulling one way is tension, and pushing, in a rod, the opposite of tension is what we call thrust. We see that less. We're going to deal with tension a lot. I almost spelt it wrong there. We're going to deal with tension a lot, and this a little bit. We're going to deal with friction a lot, and in every diagram we draw, we're going to be doing weight and reaction forces, and those are the main forces. That's enough to take you through chapter 8. Do some of the questions, read the glossary, but I'm going to be explaining bits as we go through the next chapter that go through the next lesson. I'm going to look at some real maths and do some real questions. Okay, and I hope that helps. Thank you very much.